Hello, students. So, welcome to an introduction for Unit 3, Day 3, Linear Applications. These are more word problems, and there are going to be 3 types of word problems we go over in this unit. So, I'm going to do one of each today. This video is going to be a little longer because there's going to be a little extra explanation. So the first formula that we are going to use is a distance formula. It's not the distance formula. It's a different one. It's the distance that it's how you would measure like how far you've driven after X amount of hours if you're going this speed, right? So the formula we use is called distance equals rate times time. We take the rate. A lot of the times it's going to be miles per hour, so it's kind of like a speed. And we're going to multiply it by however long you were going, okay? So I like to use charts to help me set up my problems. In fact, I'm going to copy that chart right now. And I'm going to paste the image under number 1 so that I can actually use that chart to fill out while I'm doing the problem. I will explain more about what this all means. There's 3 different types of distance problems that we are going to talk about. The first problem we are going to do, I call a there and back problem. So that's what I'm going to do in the video, and then we'll do another type or a couple types in class, okay? So you will understand how to use this chart as we do a problem, okay? So the first problem says, on a vacation trip, Jake averaged 50 miles per hour traveling Denver to Minneapolis. Returning by a different route that covered the same number of miles, he averaged 55 miles per hour. What is the distance between the 2 cities if his total traveling time was 32 hours? So don't get your phone out and just Google the distance from Denver to Minneapolis, because that's not what we went off of. This is kind of a hypothetical, okay? So we have our chart. And we are looking for the distance, so we don't know that for right now. We're going to kind of leave that area blank. But what I do know is that on the way there, okay, on the way there, he was averaging 50 miles per hour. That is a rate, okay? So the 50 miles per hour is a rate on the way there, okay? We don't know how long it took him to drive. There's a lot of unknowns. So I'm just going to call the time X because we don't know how long it took, okay? We do know that the total time was 32, but that doesn't mean that it's 16 and 16, right? Because he was going slower on the way there. On the way back, he was going 55 miles per hour, okay? So that's the way back. Now, we don't know the time, but we know that it has to add up to 32. So no matter what, the time coming back is going to be 32 minus however long it took there. So let's say it took 20 hours to go there. Well, then it would have to take 12 hours to come back because the numbers have to add to 32. So if it takes X hours there, then to find the hours back, we'd have to do 32 minus whatever that first one is. So that's where I came up with the 32 minus X. All right? That's all we know right now, except for one extra fact that it covered the same number of miles. So we don't know what the distance is, but we know that it's the same. Okay, so for there and back problems, the distance there is exactly equal to the distance back. Well, to calculate distance, we do rate times time. So for the way there, the distance is going to be 50, which is the rate, times X, because that's the time. And for the distance back, it's going to be rate times time again. But the rate for this one is 55, and the time is 32 minus X. So this is the equation I'm going to solve. I'm going to do that up here. So it's going to be 50x, the distance there, has to equal the distance back, which is 55 times 32 minus x. So distributing the 55. On the left, I still have 50x, And on the right, I'm going to have 1,760 minus 55x. No, I did not do that in my head. I have an answer key right in front of me here. Okay, so to keep solving, I'm going to add over this 55 to the left to make 105x equals 1760, or 1,760, and then divide over the 105. So x equals, it doesn't come out nice, that's okay, 16.76 hours. Now guys, that's not answering the question. What was the question? The question says, what is the distance? I know the time that they drove, but I don't know the distance. So to find the distance, I can plug into either distance equation, 50x or 55 parentheses 32 minus x. Because we set them equal, it doesn't matter. So the distance, I'm going to use the first one, that's easier, is 50 times x. So that's going to be 50 times 16.76. And that is 838.095 miles. And that's the distance. So these problems are tough because a lot of the time you solve for one thing, but you're actually looking for a different answer. So you have to go back, read the problem, and understand what to plug in. All right, so if you were like, wait, what? That's why I'm filming this. So you can go back and watch it again, and I can re-explain it to you in class. This is just an introduction, but that is a distance problem with a there and back. The next type of problem we're going to do is called a work problem, okay? And the formula is going to sound a little familiar. It's also work equals rate times time, but the rate is a little bit different than the rate from above. So it's not going to be like a miles per hour, okay? But it's going to be a special kind of way to get it. So see if you can follow along. I'm going to copy this chart. Here's the chart that I like to use for this kind of problem. Rate and time. All right, couple things to note. The work is always going to equal 1. The work is always going to equal 1 because what that means is I want 100% of the job done. 100% written as a decimal is 1. Okay, so that is what I'm always going to put in for the job or the work. Okay, and work is equal to rate times time. So when I do the rate, and I wrote this down, it's going to be the individual time that I'm given, and I'm going to have to put that under the number 1, and that's because I need to convert it to per hour. I'll explain that as we do the problem. And when we talk about time for the chart, we're talking about the total time it takes to finish the job together. And we want 100% of the job done, so whatever the rate times time is, we're going to add those together because it's more than one thing working together, and we're going to set equal to 100% or 1. All right, so that's the idea. Let's do a problem. It's pretty simple. If Tom can paint a room in 3 hours and Sue can, it should say paint the same room. Dang it, I thought I fixed that. Can paint the same room. We're painting, not cleaning. I changed it to paint because I thought painting a room in 3 hours or cleaning a room in 3 hours or 5 hours would be awful, but painting seems more realistic. So Sue can paint the same room in 5 hours. How long would it take them to paint together? Okay, it's obviously going to be faster since there's 2 people working. So we have 2 people. We have Tom and we have Sue. Tom's rate, we need to get it to per hour. Yes, he can clean an entire room in 3 hours. So how much of the room can he paint in 1 hour? Well, if it takes 3 hours, then 1 hour would be a third of the room. So the trick is to take his individual time and put it under the number 1 so that we do it per hour, okay? Whereas Sue can do it in 5 hours. I would argue that I clean my house much faster than my husband, so my time would probably be faster. But again, we're not talking about cleaning, we're talking about painting, whatever, he could probably paint faster. So I guess fine. But 5 hours for Sue is going to be 1/5 per hour. All right, so then the time is what we don't know. We don't know how long it's going to take them together because the time in the chart is the total time together. So I'm going to call this X, or I can even call it T for time, or X, whatever you want to do. Now, the work for Tom is 1/3 times T. The work for Sue is 1/5 times T. So since they're working together, I'm going to add these up, and I'm going to set this equal to 1 because I want 100% of the room clean. That's the setup, guys. That's it. Now I just have to solve. So I personally would clear the fractions by multiplying both sides by 15. So 15 times 1/3 is 5, so 5t plus 15 times 1/5 is 3, so plus 3t equals 1 times 15 is 15. So I get 8t equals 15 and divide both sides by 8 to get t equals 15 over 8, which is about 1.875 hours. I do not need you to convert to hours and minutes, but it makes sense that they would paint the room much quicker than each individual time because they're working together. So that is the answer. The last type of problem is I call them mixture problems. The other teachers call them chemistry problems, but same difference. And this is the formula that we're going to use. It's the percent times the amount for the first chemical plus the percent times the amount of the second. And we're going to set that equal to what we need. Okay, so this is the setup that I use for chemistry or mixture problems. All right, so it says Jenny is a chemist. She needs a 20% solution of alcohol. She has a 15% solution on hand as well as a 30% solution. How many liters of the 15% solution should she add to 3 liters of the 30% solution to get the 20% solution? Whoa, when you read it, it's a lot of info. That's why I use the chart. I like to break it down and make it as easy as possible. Well, I see the word needs. She needs a 20% solution. So the percentage we need is 20. I don't know the amount yet, so I'm going to leave that. She has a 15% solution. So that's one of the has. She also has a 30% solution. So that's another have. Okay, good. We're done with that part of the chart. It says how many liters of the 15. So that we don't know. I'm going to put an X there. Should she add to 3 liters of the 30? All right, so then what do we do for the amount for the needs part? Well, think about it. If I pour 3 liters of the 30% into a bucket and I mix it with X amount of liters, then the total I'm going to have is X plus 3. So you just add the amounts together for the need part. And it's always going to be like this. It's like the same thing every time. The setup is this. We're going to add this mixture. So that's going to be 15 times X. We multiply those. So we're going to add that to the second mixture, 30 times 3. And set it equal to the need, 20 parentheses X plus 3. Okay, let's do some math. So we have 15X plus 90, 30 times 3 is 90, equals 20X plus 60. So I'm going to subtract the 20X to the left, which gives me a negative 5X. Subtract the 90 to the right. That's negative 30. I could have gone the other way, but it doesn't matter. Equals divide the negative 5 over, and I get 6. So x is 6 liters. And the question, always go back to read the question, just in case it's not asking for just x. The question is saying how many liters of the 15%. So that's just x. If the question said, how many liters will I have in the end with the 20% solution, then that answer would be 9 because I would have to plug in to this, okay? And 6 plus 3 is 9. So that's the idea with the mixture problems. Hopefully some of that made sense, but word problems are intense. There are a lot to kind of grasp, so if not, that's okay. That's why we're just doing an intro and we're going to do more problems together in class. Thanks, guys.